So now we get to the third stage of integration. After we've determined that we can't use the power rule, or after we've determined that we can't use substitution, then we would try integration by parts. Now, the challenge with integration by parts is there's really no hint in the function itself or in the integral itself that integration by parts is the method to use. Integration by parts is simply going to be used when we're integrating a function times another function. But so is integration by substitution. So there's no real tip-off. And in addition, there doesn't necessarily need to be any relationship between these two. I mean, there's in integration by substitution, one of the functions would be there, and its derivative would be in the other part, right? But integration by parts, we don't have to have that relation. So here are three integrals that we handle typically by integration by parts. And you see that we can't make a u substitution like letting u equal x and find the derivative of our substitution sitting right next to it, right? Or u equals cosine, the derivative of cosine, which is negative sine, is not sitting right next to it. So in each of these cases, substitution doesn't work. So how do you know when you can use integration by parts? Sadly, the answer is simply after you've determined that it's not a power rule problem, after you've determined that substitution won't work, and we know that substitution won't work in these cases because we don't have the u du pairing, right? Then you try integration by parts. Beyond that, there's not much indicator, right? So you kind of have to get to integration by parts after eliminating the other two options. Now you might, in general, you might say things like, well, integration by parts you have is helpful or is possible or is probably a good choice if you have, say, a polynomial term and then some cyclical term like cosine or sine, polynomial term, and then e to the x, right? That's kind of cyclical. It just is this. It's its own derivative, or a combination of the two, right? But really, I don't know that those are real helpful tips. I just say that if you can't use power rule or substitution, then try integration by parts. All right. Finally, that brings us to our last kind of method of integration, and in reality, this one is one that kind of we could use at any stage. And this is integration, we'll just call it integration by using tables or formulas. There are some integrals that we cannot typically attempt to do without just looking at a table and seeing what the integral is. A real simple example, the integral of sine, right? Super simple. That's negative cosine. Right? We just know that because we've learned that rule. Now, yes, we could derive it using the limit definition of derivatives. But in reality, we generally function by just knowing the antiderivative of sine is negative cosine. The antiderivative of cosine is sine, and so on. So we have just these rules that we've memorized. And that's what I mean by tables or formulas. And there are a variety of those. All of our trig ones. Then we have things that look like this, right? The integral of dx over square root of a squared minus x squared, and that is equal to the inverse sine of x over a. You can derive it, but it's typically we just remember the pattern. We just have to kind of recognize, oh, I've seen that pattern before, and we look in our tables or look in our formula sheet, and we see that's the inverse sine. So there are a variety of those that we just have to remember. And of course, we can use these integration by tables at any point in the process. All it takes is for us to recognize the integrand is one of those formulas. All right. So I'm going to throw in a bonus here, and this is actually not a method of integration. Well, it's a specialized method of integration, one that we don't use very often, but every once in a while we run into it in in linear or in differential equations. And this is integration of rational functions by partial fractions. Okay, integration of rational functions. So let's stop there. This is a specialized type of integration. None of the other methods work here, but we're integrating rational functions. So real simple example, I wouldn't say necessarily simple, but something like this. 5x minus 3 over x squared minus 2x minus 3 dx, right? So that's a rational function. It's not going to be, we're not going to be able to use any of our previous methods to integrate this. So the approach is to break it down into its partial fraction decomposition. Okay, now that's something you're going to have to, you might want to check in and review. I wouldn't say do it right away, but maybe when the time comes if you run into a problem like that. And what we realize is this rational expression using partial fraction decomposition can be broken down into this right here. And again, I'll let you review the details of performing partial fraction decomposition. But once it's in here, then this is, we can integrate each of these different pieces separately by substitution, and we'll end up with, 2 ln of x plus 1 plus 3 ln of x minus 3 plus c. Okay, because you get it, once you get it to this point, you should be, you hope you can use substitution or one of the other methods that we've got. But the trick is to rewrite the rational function in its partial fraction decomposition. We'll see that once in a while, so I just want to bring that to your memory, so that if you run into one of those rational functions, you can try this approach.